Welcome to RISE Learning Machines seminars. RISE, Sweden's public research institute with more than 3,000 people working on a wide array of research topics. The computer science department works on applied AI projects for the benefit of society, and we organize these weekly Learning Machines seminars. This meeting will be recorded, and if anyone wants to be removed from this recording, let us know. Also, make sure to check out our great collection of talks with many interesting topics on our YouTube channel. Today, I am very happy to introduce Valentin De Bortoli, who is a researcher at Google Deepmind in London. Valentin defended his PhD in 2020 at ENS. He's been a postdoc at University of Oxford and a research scientist at CNRS. His research interests are regarding stochastic methods for generative modeling, and the topic today is Diffusion Schrödinger Bridge Matching.
Okay, so yeah, so on that I'm going to get started. Today I'm going to talk about something that I've been working on for the past 3 years now. So this is a line of work that I started when I did my postdoc at Oxford University, and I've been working on that ever since, which is really linked with this diffusion model that are now extremely popular in generative modeling and for other stuff too. So this is joint work with a bunch of people from Oxford University: James Thornton, Jeremy Heng, Yuyang Shi, Andrew Campbell, and Arnaud Doucet. So yeah, so the concept that I'm going to talk about today, so by the way, sorry, there was supposed to be a video, but for some reason the video is not showing, so it will have to do without the video. So the talk today will be about how can we leverage diffusion models to solve some tasks that are not generative modeling. The tasks I'm going to talk about are inverse problem, and more specifically, every task that can be solved with transport. So here I'm going to talk about optimal transport, and I'm going to give you kind of a framework of why optimal transport I think is a good notion here, and how we can leverage that to solve this kind of inverse problem that come up in a bunch of situations. So really the goal of my talk is not really to do an introduction to diffusion model, although I'm happy to take questions and like to clarify stuff about that, but to show how you can apply them to do other stuff. So just one slide of recap on diffusion models. I really do think that I mean, I know it's a bit that's deliberately controversial, my title at this slide. They really exhibit very, very good capabilities across a large range of tasks in generative modeling. And so, yes, there are still a few problems with diffusion models. In particular, I think it's still an open problem, the fact that they are quite slow at inference time. But more or less, they have been a huge improvement. They represent a huge improvement over previous generative models that we have, like what we had with GANs, what we had with VAE or normalizing flow. So just to recap maybe a little bit, so generative modeling is the task of starting from, let's say, a simple distribution. I want to be able to create new sample from a data distribution. And the data distribution, usually I have access to it not through a normalized density. I have access to it through samples, so my data set, really. And so that's why we are doing machine learning and not like statistical sampling, right? So diffusion models on that task have been excellent, and they really rely on this concept of iterative refinement, where you're going to start from a Gaussian distribution, and then you are going to progressively denoise that Gaussian distribution in order to create samples from the target data distribution. So even if you don't know diffusion model, just in 2 lines, what they do is you have a forward process that is going to corrupt the data. So you start, let's say, with the sample of your data distribution. So let's say, I don't know, the image of a cat, the image of a dog. And then you're going to corrupt that image of a cat with some Gaussian noise. And usually what you apply is what we call VP-SDE in the field of diffusion model, but which is really Hochstein-Lembeck process that is going to progressively destroy the information towards the Gaussian. So you are interpolating between your data distribution and a Gaussian. So that process is non-parameterized at all. This is completely given. It's really easy to destroy data. But what is hard now is to say, okay, well, I'm starting now from my Gaussian, and my goal is going to try to revert that forward noising process. And I want that backward denoising process to invert the forward. Of course, that is hard because now you have to solve a bunch of denoising problem. But this is exactly what diffusion models do. You have a loss function that is a denoising loss function that is averaged across times, and then you use the denoiser that you have computed to progressively denoise and to get good-looking samples. Okay, so diffusion models have been, now used for image. Stable diffusion works on that. ImageN works on that. A bunch of applications in protein as well. So, for example, what is nice is that the diffusion models can be extended to a broad scope of data, meaning that as long as you are able to define a forward noising process and a backward denoising process, you are almost done with the diffusion model. And so, for example, diffusion models have been extended to Riemannian manifold, for example, to do protein modeling. So there is a paper on that called RF diffusion, which exhibits like really, really good properties. But that's just to show you, kind of showcase the capabilities of diffusion model. Okay, so diffusion model, they solve kind of the task of generative modeling, where your initial distribution is going to be some Gaussian and you target some data distribution. But there are a bunch of other applications that I think are quite interesting, which cannot be solved with these models. I think maybe the one that I think about the most is inverse problem, where you don't want to start from a Gaussian, you want to start from another data distribution and go back to the data distribution. So you can think of it as, let's say you want to do some deblurring, and you would start from the blurred image and you want to go back to the unblurred image, or super resolution, where you start from the low resolution image and you want to go to the high resolution image. So all these transfer tasks, yes, you can use somehow the idea of diffusion model to solve that, but it's not very satisfying in the sense that you would like to leverage some interpolation not between the Gaussian and the data distribution, but the interpolation between two data distribution, one being the clean samples and the other one being the blurred sample, or the degraded samples. And once you are in that setup, there are two questions that arise immediately. The first one being, okay, so I have a data set of one data distribution. I have another data set of the other data distribution, right? I have access to samples. Are these samples paired or are they unpaired? So if they are paired, that means that you have a data set of when you take a sample of that data set, you have a clean image and you have the corresponding blurry image, right? Or more like it, you have a blurry image and you have the corresponding clean image. So that's the paired setting where you know the coupling between these two distributions, right? Like in terms of transport, this is like amount to knowing the coupling beforehand. And then you have the unpaired transfer task, where you just have two distributions and you don't even know or they are coupled. So there are a bunch of applications of that. I'm going to talk about one in the next slide. Most likely in climate science, we have a nice application of this stuff, but there are a bunch out there. So when I'm talking about Schrödinger bridge, which is my main area of work, I'm talking about unpaired transfer task. And there is this progression, I think, in terms of like relatively easy to more and more difficult. You start with generative modeling when you interpolate between Gaussian and data distribution. Then you move to paired transfer task where you have access to the coupling, but now you're trying to move from one data distribution to the other. And then finally, you move to unpaired transfer task where you have just two data sets and you're trying to find some meaningful interpolation between between these two data sets. Okay, so that's kind of the setup that I'm looking at. And today I'm going to talk about how you can solve the unpaired transfer task problem using optimal transport and diffusion model. Okay, just before I dive into the method and like the use of optimal transport, I just want to say a quick word about the unpaired transfer task. So something that I really like is this example from climate science, where it's a super resolution task, where you have some simulation at high resolution of some vorticity field, and you have some simulation at low resolution of the same vorticity field. So you could say, okay, well, that should be easy. That should be a paired data set, because if I can simulate a high resolution vorticity field, then I should be able to have the low resolution one. The problem is it's not that easy, because the simulation at low resolution and the simulation at high resolution don't necessarily agree, because you don't have a simple, operator that goes from the high resolution to the low resolution. This is because like Navier-Stokes equations are highly nonlinear, and also you have boundary effects that need to be taken into account and that depend on the grid size. So really what usually people have, and this is what is advocated in that paper from Bischoff and Deck, what they say is that in this field of climate science, usually you are in the unpaired setting. So we do have applications in the unpaired setting which are quite important. Okay, so before, so that was kind of for the setup. Now I'm going to dive into optimal transport, trying to present what are the tools that I'm going to use and why I think for unpaired transfer task, optimal transport is well suited for that. Okay. Again, if you have any question on the background, don't hesitate to interrupt me now or later. I'm happy to take question whenever. All right. So yeah, so if there's no question, let's move on to optimal transport. I'm going to give a very quick introduction to optimal transport. My goal here is not to dive into the theoretical side of it. I just want to show you how you can move from an unpaired problem to optimal transport, and more specifically, the notion of Schrödinger bridge. So remember, what is the unpaired transfer task setting? I have two data distribution that I'm going to call pi0 and pi1. Okay. I don't have any coupling between the two. And my goal is twofold. I first want to learn a good coupling in some sense, between pi0 and pi1, which I'm going to call capital Pi here. And then I want to learn how to sample from that coupling. So sampling from that coupling, what does it mean? At the end of the day, I want to be able to take a sample from pi1 and be able to get the corresponding sample from pi0. So again, assume that you start from the low resolution climate science image. You want to be able to sample from the corresponding high resolution climate science image. And optimal transport, in a way, is doing exactly that. So here I'm presenting it with the Monge formulation, where the objective is in the boxed equation here. What you are simply trying to do is you are trying to find a mapping T star, and this mapping T star should minimize the following objective function. So it should minimize the cost. So the cost here being some kind of measure of similarity. For simplicity, just think the squared L2 norm. So just think of it as T. You want to minimize on the whole, sorry, it should be, it's not dx here, it should be d pi0 of x. The integration should be with respect to pi0, my bad. So you want to find a t which is going to move x as little as possible. This is what is given by this integral here that I want to minimize. And the other requirement is that t star must transport pi0 onto pi1, right? So this is the push forward of pi0 should be equal to pi1. Okay. So again, just to summarize, the first thing with the cost tells you how much I pay to move x using t, and I want to do that, and I want t of x to be as close as possible as x with respect to some cost. And I also have the constraint that t star should push pi0 onto pi1. Okay. By the way, if you were at ICML 2023, there's a really nice tutorial by Marco Couturier and Charlotte Boone on this type of static formulation. Okay. So this is all good and well, and there are like methods to try to estimate that. But we know that these methods, when we look at the Monge formulation, they are quite fickle in the sense that they are really sensitive to pi0 and pi1, meaning that if I change pi0 by just a little, then it will completely change T star. So this is really bad for machine learning, because in machine learning, we expect to have some kind of regularity, or at least some kind of continuity in our solution. So T star, if you imagine that now being parameterized by a neural network, that means that your neural network should learn to have like very sharp constraint. So a way to kind of get away from that is to introduce some kind of regularization. Okay, so before I introduce this regularization, I need to kind of define another setting for the Monge formulation, which is called the Monge-Kantorovich formulation, and which is equivalent in a lot of settings to the Monge formulation. So instead of trying to estimate a mapping T that is going to transport pi naught to pi 1, I'm now trying to, it's exactly the same function as before, exactly the same loss function, sorry, as before, except that it's not a loss function on T, it's a loss function on the coupling pi directly, capital Pi here. And my requirement is that pi naught is equal to pi naught, and pi 1, well, capital Pi 1 is equal to pi 1. So what you are trying to do now is you can have a stochastic assignment, right? And what happens is that usually the solutions are the same between these two problems, but with this formulation, now what I can do is I can do the following. And by the way, there is a typo. It should not be a plus. It should be a minus. Sorry about that. Where not only I'm going to regularize that functional by putting a little bit of entropy. So not only I'm trying to push to minimize the cost. So I still have the requirement that pi naught is equal to pi naught and pi 1 is equal to pi 1. But now I have the additional requirement that, yes, I should minimize the cost, but I should also try to somehow maximize the entropy. And this depends on some kind of regularization parameter epsilon here. And this stochastic version is much more stable. So if you know about the Synchron algorithm, the Synchron algorithm is a very famous algorithm that is used to solve this type of problem, at least in discrete space. Marco Couturier has worked a lot on that, and this Synchron algorithm and using this entropic regularization has a lot of nice properties. In particular, you have very fast solver for this type of thing. So, okay, so now we have something that is a bit more amenable for machine learning techniques, in the sense that the solutions are more regular. But diffusion models still seem to be quite far away. In particular, now I just want to take a step back and want to think about what are the requirements to make this formulation, this minimization problem, akin to some kind of diffusion. So in diffusion model, when you think about it, there is the main requirement is that we are doing this type of iterative refinement. So we had a problem that was transferring a Gaussian to the data distribution. We could have tried to do that in one shot, right? Just sending the Gaussian samples to the data distribution sample. But what we do in diffusion model is that we have this dynamic approach compared to a static one, where we progressively denoise the Gaussian noise to get back to the data distribution. And here, what we have is that we are in this static setting in optimal transport, where we have this function here, and the coupling that we have is a coupling that sends us that is going to take pi naught and send it directly on pi 1. There is no notion of like process or like something being dynamic here. And so what we do is, I mean, very smart people have thought about this, and there are actually a way to move on from this static formulation to a formulation that is dynamic. And this is exactly what Schrödinger did back in the 1930s, even though he didn't have the right language to talk about this stuff at the time, but this is exactly what he did. So I'm just going to present very quickly how to move to the dynamic formulation and what it is actually. So the static formulation is, I just repeated it, and I repeated it actually with the typo, so this plus should still be a minus here. So let's say that you have pi star here. Pi star is the solution to your static formulation. What you have is that I can find a dynamic problem whose solution that I denote p star is going to coincide somehow with pi star. Okay, so this dynamic formulation is the following. So just please note that the cost here, now I'm using the cost that is only the squared norm. I'm not using something else than the square norm, okay? My cost is always going to be this L2 cost. So now assume that you have, that you are looking at the following problem, but not on the space of coupling. Now I'm looking at distribution on the space of function. So on the space of continuous function, such that, so this is what we call a path measure. A path measure is a probability measure on the space of continuous function that are indexed by time. So let's say that a Brownian motion, for example, a Brownian motion that starts at time 0 and ends up at time 1, a Brownian motion is an example of path measure, okay? And actually what I'm going to look at is Q here. Q is the path measure, so it's the distribution associated with here a rescale Brownian motion, okay? So let's say that you have this rescale Brownian motion and the associated path measure. Right, so what I'm going to look for is I'm going to look for path measure P that is going to be as close as possible with respect to the Kullback-Leiber divergence to Q. So I want to look for a path measure that is as close as possible to this rescale Brownian motion, such that P naught is equal to pi naught and P1 is equal to pi 1, okay? And what we can show is that if I manage to find such a path measure that I'm going to call P star, so P star is, again, a measure on the space of continuous function. If I look, so for example, here in blue, I've just shown, for example, one sample path of P star, and I'm going to call xt this sample path. If I look at x0 and x1, then they are samples from the solution of the static problem. So again, this is a way to link a static problem to a dynamic one. But now that we have a dynamic problem to solve, mainly to find this kind of path measure, this is how we're going to build a connection with diffusion model and like iterative refinement and ways of building stochastic process. Okay, so the dynamic formulation, again, it's called the Schrödinger bridge. It's the Schrödinger bridge problem, actually. And this is what we're going to look for. So now you can even forget about what I said about optimal transport. You can just think that our task now is to find a path measure, so a stochastic process really, that is as close as possible to a rescale Brownian motion and which has the right starting distribution and the right terminal distribution. Okay, so again, as I was saying, P star is called the Schrödinger bridge. Now, there is one last point that I should address that is going to be useful later on. So I just said that if I manage to find P star, I do have pi star. So if I have the solution to the dynamic problem, I have the solution to the static problem. It turns out that the converse is true. So if you have a solution to the static problem, you also have a solution to the dynamic problem. How come? So what you have is that if I'm given pi star, to sample from P star, what I'm going to do is I'm simply going to sample x0 and x1 from pi star, okay? And then how do I sample a trajectory from that? Well, if I now just want to sample xt with t between 0 and 1, so and t being distributed as p star t, so p xt being the marginal of the path measure at time t, what I can simply do is interpolate linearly between x0 and x1 plus add a little bit of noise. And the noise that I'm adding is proportional to the square of the regularization parameter. So when we have this property that whenever I'm going to condition, well, to sample from P star the path measure, I just need to sample from the extremal points, so the initial distribution, the terminal distribution, and then I can recover any point in between by interpolating using this kind of linear interpolation. That is to say that P is in the reciprocal class of Q. So there has been a lot of study in math and probability about what is the reciprocal class. But here I'm just going to use that definition that P is in the reciprocal class if it satisfies this thing that whenever I condition P by the endpoints, I can recover any point in the trajectory by interpolating. Okay, so that's what I call being in the reciprocal class of Q. And the very neat thing, and that I'm going to use a lot in the rest of the talk, is that I defined the Schrödinger bridge as a solution to the Schrödinger bridge problem, right? So the Schrödinger bridge was the minimizer of some loss function. So the minimizer of this function, it was the minimizer of the Kullback-Leibler divergence between P and Q under some constraint. Well, it turns out that the Schrödinger bridge can also be defined as the intersection of 4 different properties. These 4 different properties are the following. First, you want your path measure to have the right distribution at time 0. Okay, that's good. Second, you want your path measure to have the right distribution at time 1. That makes sense. Third, you want your path measure to be Markov. That means that it's not going to depend on the future, and it's not going to depend like deep in the past. It's just going to depend on the present tense. So that's just a Markov property of the path measure. And then you need you need the path measure to be in the reciprocal class of the Brownian motion. If you manage to find a path measure, well, under some mild assumption, if you manage to find a path measure that has both the end and the starting distribution to be fixed, that is Markov and is in the reciprocal class, the only possible thing is that you are the Schrödinger bridge. So to find the Schrödinger bridge, really what you just need to do is trying to project on the intersection of these 4 classes. And this is exactly what we have been working on for the past 3 years, basically. So what I'm going to present now is one algorithm leveraging diffusion model to do exactly that. But the goal of my presentation was more, not maybe to advertise for our algorithm, but I just wanted to, for me, that is the core of this presentation. I just wanted to present you kind of the setting and to show you that we can move from unpaired transfer task to optimal transport to a dynamic formulation of optimal transport that is now really akin to what you would do in diffusion model. So yeah, if there are questions, again, don't hesitate to interrupt me. Otherwise, I'm going to move on to one of the algorithms that we proposed. So the algorithm that we proposed back in 2021 was leveraging what is called iterative proportional fitting. So if you come from the optimal transport community, you know that iterative proportional fitting is the same thing as the synchron algorithm, just a different name, and usually the synchron algorithm is given on discrete state space, whereas the iterative proportional fitting algorithm is just given, like on arbitrary measure space. Right. So let's have a look at what the iterative proportional fitting algorithm does. So the iterative proportional fitting, so IPF for short. Now, when I say IPF, I mean iterative proportional fitting. The IPF is going to start with the Brownian motion. So the Brownian motion is something that is Markov, and of course, in the reciprocal class of the Brownian motion, because it's in its own reciprocal class. So two of the first properties, I mean, the Markov and the reciprocal properties are satisfied. And I'm also going to start my Brownian motion at pi naught, okay? So I have 3 out of 4 properties that are satisfied to find my Schrödinger bridge. And now what I'm going to do is I'm going to alternate projection between projecting my path measure on the set of path measure that have fixed initial distribution and path measure that have fixed terminal distribution. Okay, so this is what I'm going to do. I'm going to alternate the projection here. And the nice thing is that during all this projection, you can actually show quite easily that the Markov property and the reciprocal property are preserved. So that means that, I mean, there is a way to prove that at the end of the day, after all my projection on these 2 sets of constraint, I will get a path measure that is the Schrödinger bridge. All right. But now there is the question, of course. So I started with a Brownian motion with fixed initial distribution. How can I move from a stochastic process that has fixed initial distribution and find the closest stochastic process that has fixed terminal distribution? Meaning, like, I want to do the projection on the space of path measure which have fixed endpoint. Well, there is a way to do that. And the way to do that is exactly saying, okay, I'm just going to keep my dynamic. So let's say I start with a dynamic P, and I want to project this dynamic on P1 equal pi1. What I can just do is I can just try, okay, to change the endpoint of my dynamic. So I have a forward dynamic, and now I'm going to change the endpoint. But it's really hard to sample from that, right? Because I don't know how to sample. So far, I'm assuming that I can only sample forward from this path measure P. Usually think of it as like having a Brownian motion. You cannot sample easily from a Brownian, well, you can, but like, let's say you have an arbitrary dynamic. You cannot sample easily from that arbitrary dynamic condition on the distribution at the end being fixed. But what we can do is, if instead you have this forward dynamic, you write it backward, then now your condition on the endpoint becomes a condition on the initial point for the backward dynamic. And so let's say now that you are able to compute what are the coefficients of this backward dynamic that is associated with this forward dynamic, then it just means that you need to start the backward dynamic at pi1. And this is exactly what you do when you train a diffusion model. Remember, a diffusion model, you have a forward process, and then you try to revert that process starting from a Gaussian. Here we do exactly the same thing. We have a forward process, and then we try to revert that process, and we start that process at pi1 in our case. So that means that we need to compute the time reversal of xt here, of xt, which is the forward dynamic. We we compute the time reversal, and turns out that, you know, if you know diffusion model, there is a closed form solution for the time reversal of the forward, which is given by this, and then you have this thing to learn. So the score function needs to be learned, and once you have that, you have managed to project your forward dynamic with fixed initial distribution to a backward dynamic with fixed initial condition. And so you have changed your forward dynamic into a backward dynamic, and then you repeat the process. And when I say repeat the process, is that first you start with a forward dynamic with such that P naught is equal to pi naught, and then you get a backward dynamic with fixed starting point at pi1, and then you're going to project that again to get a forward dynamic with fixed starting point pi naught, etc., etc. And so what happens when you do this type of alternate projection is that now, instead of only parameterizing the backward, you also parameterize the forward, and basically the forward is going to give you all the information you need to train the backward that you train, and then you train your backward that is going to give you all your information you need to train the forward, and you alternate between the two. So really, this algorithm that we call diffusion Schrödinger bridge is an algorithm on which we iterate the training of two diffusion models which inform each other to sample to find the Schrödinger bridge, and then to solve this type of unpaired transfer task. So I'm not going to dive into how we set the loss function here. The loss function is just the classical loss function that you would have, well, one of the classical loss function that you would have in diffusion model to learn the backward. And so you alternate between the training of the forward and the training of the backward and the training of the forward. Okay. So sorry, I forgot to change color on the last slide, but basically you just alternate between that and that. So you have two networks, one that controls your forward again, and one that controls your backward. And you just noticed, sorry, that there is a typo. Theta and phi, sorry, do not correspond to what is written below, but okay. Apologies. Oh no, actually they do, sorry, my bad, apologies for that. So you sample from the forward, so xt, when I use the letter xt, it always means I sample from the forward, and v phi is associated with the forward, and when I sample from the forward, I train the backward. And this really corresponds to doing this type of alternate projection. You can have guarantees that this process is going to, well, if you assume, if you're willing to assume that your network are perfect and that they perfectly learn the dynamic, then you can prove that this procedure actually does converge toward the Schrödinger bridge, and you can even do some kind of computation to show that even in practice, you recover the optimal transport in some setting for which the optimal transport is known. So I'm going to skip this part just in the interest of time. This second part is about a new algorithm that we have from this year, and that is going to appear at NeurIPS. I mean, it's on arXiv, but it's going to appear at NeurIPS as well, which leverage another kind of projection. And it leverages another link that you have between Schrödinger bridge and a class of model called flow matching. So flow matching is this kind of new class of model that is an alternative to diffusion model, even though there is a non-zero intersection between the two. But it kind of corresponds to do the projection in another way. So now instead of projecting on pi naught and pi 1, we project on the path measure which are Markov, and the path measure which are reciprocal. So it seems to be more complicated at first, but it turns out that it's actually quite simple to project on Markov measure, just leveraging the Girsanov theorem, and projecting on reciprocal measure is also quite easy. So this algorithm works very well in practice, this new algorithm. So we call this procedure, because I don't think it has been that much studied in the literature. I'm happy to be wrong on that one, though. We call this new procedure the iterative Markovian fitting compared to iterative proportional fitting. And the associated algorithm that we have and that we implement is called DSBM, so Diffusion Schrödinger Bridge Matching. The matching part corresponds to, there is a reference to this new type of procedure that is called flow matching, if you're familiar with that. But you can just think of it as another way to solve the Schrödinger bridge problem. And so the task is the same. We still want to solve unpaired problem. So we want to solve unpaired problem, and these two things are just two ways of finding the same solution by doing two different types of projection. Right, so I'm going to skip that. And just going to switch to the example just to show you what kind of results you can expect with that. So again, there is this setting. Again, I'm going to talk about the climate science experiment where we have a goal. Our goal is to do super resolution, which in climate science is sometimes called downscaling. The goal being like, I have cheap low resolution simulation and I want to upscale them, downscale them, like at the super resolution of this small resolution simulation. And what I want to do is I want to find, so this is an unpaired task, and I want to find something that is both plausible in terms of simulation and is also close to my low resolution simulation. Okay, and again, this is a really unpaired problem. So just to give you a little bit of information about the data, the low resolution is 64 by 64 by 2. So these are just like two channels of the data. And the high resolution data is 512 by 512 by 2. So again, these are just the two channels of the data. And you see that it's actually quite a complicated problem because you have a lot of vorticity here and here. So you have a lot of fine details that you have to reconstruct with the neural network. So it's really not a trivial task to find something that exhibit both really good properties in terms of quality of the samples, and also that is close in the L2 distance from the low resolution. Okay, so I'm sorry, I had the video here that I'm also gonna skip, and instead I'm just going to dive into the conclusion. I just want to kind of summarize what I've been talking about so far. My main point was to say diffusion models are really good for generative modeling. They are not, I think, they are not enough when it comes to paired and unpaired transfer tasks, and there is still room for methodological improvement there. In particular, I think that Schrödinger bridge and optimal transport can be used and can be leveraged for this type of unpaired transfer task. In particular, I think, especially for this climate experiment, we get like state-of-the-art result by really not playing around too much with the algorithm. It's kind of like out of the box, it just works. So that's good news. So yeah, that's kind of the setup I wanted to present. I have these two algorithms that I've been developing with my co-authors. So one leveraging the IPF, which is called DSB for Diffusion Schrödinger Bridge, and one based on the IMF, so this Iterative Markovian Fitting, that we call DSBM, so Diffusion Schrödinger Bridge Matching. And what is, I think, quite interesting is that these two algorithms exhibit a lot of links with the existing literature on diffusion model and flow matching. Of course, there are a bunch of challenges here. I don't have the time to really talk about them in detail, but just to let you know, there are a bunch of work that should be done on making these models faster, and especially the training of these models, because compared to diffusion models, there is still quite a big gap to fill. They are scalable. They are really scalable, these models. They are just slow to train. So we need something better for that. Something that is also interesting is to try to find a unified framework for all these methods that we have so far for solving this unpaired transfer task problem. And in particular, that would be very useful for, let's say, trying to find what is the best between DSB, DSBM, IPF, etc., and like to do some more exploration and decipher a bit what are the real contribution of each one of these algorithms. So yeah, I'm gonna stop here. I'm happy to take question about anything I said during this presentation. Thank you.
Thank you, Valentin. So if there are any questions, please ask them in the chat, and I will forward them to Valentin. I'm curious about the application with the climate simulations. How well do you perform in this task? And in particular, the slide you showed early on in the presentation, it looked really challenging due to, as you mentioned, the different resolution can end up with really differing results if you have different resolutions.
Yeah. So the there is some echo.
Oh.
So
Du har dödat ditt utljud istället.
Does it work now?
Yeah, okay. There's still some echo, but
oh, sorry. There we go.
Yeah.
Okay. Yeah, so I guess my question was just like, can you just repeat the question about like, so your question was about how does the image form?
Yeah, so if you if you work on this particular problem, I see now that you're showing some results here. How should we sort of interpret this? How well does it perform when
Yeah. So I guess the what is nice with the climate science, because if you work with images, it's not clear what is a good metric for that. And here in climate science, I mean, I don't know a lot about climate science, but in that paper, Bischoff and Deck, they actually came up with a bunch of metric. So there are two types of metric. There is one which is the L2 distance between the high resolution and the low resolution. So this one just compute how far the low resolution is from the high resolution in L2, and that's an objective that they are really interested in. So that's for kind of how close the samples at high resolution are to the low resolution one. That doesn't tell you if the high resolution samples are any good or useful in any way. And so for that, we have other measurements which are based on some type of frequency that apparently are used in climate science. So they look at the spectrum of the spectrum of the images that we have at high resolution, and they check that the spectrum do match between between the samples that we generate and the actual sample from the dataset. So this is the metric that they use. To be fair, I think that is not nearly enough to capture like some kind of the fine detail of the vortices. Looking at the power spectrum doesn't seem to be enough, but visually it seems that the method that we have performs well, and on the metric that they have, these methods perform better. But yeah, I really want to emphasize that I think that it might be that also there is the need for like a better evaluation of this type of model.
Okay, thank you. Do you have some other examples of other domains where you have tried this?
Yeah, sure. So some other stuff that we have done, so that's in the paper. So I don't know if you have heard about this paper called CycleGAN, where what you're trying to do is to transfer, let's say you have the image of some pose, and you want to transfer that pose to, let's say, a human having the same pose as let's say the stick figure that you give. And so this type of transfer task, when you want to go from one image domain to the other, or you have pictures that are taken in winter and you want to transfer them to pictures that are taken during the summer, so basically remove the snow. So this is the type of thing that we've been experimenting with image. So yeah, basically, like you have similar data sets, or data sets that cover the same domain, but with different type of extra information. So one very toy example that we did was, let's say on celeb A, transferring from one class of celeb A to another class of celeb A. So if you have any image data set with some class, you can transfer from one class to the other. So yeah, that's something that we did. It's also useful in single cell genomics, where you observed two populations at different point in time, but the observation process is destructive in the sense that you cannot follow the population. So what you observe is you observe the population. You just observe the population. You cannot follow any particle, and then you're trying to reconstruct the trajectories, basically. So we do have example of that. I just want to point out and just give a quick shout out to other methods which are based on mini batch optimal transport, which actually perform very well in that same setting. Yeah.
All right. Thank you very much, Valentin De Bortoli, for
Thank
this
you.
exciting talk. I will add that in 2 weeks' time, on November 2nd, we will have our next Learning Machines seminar, and will be visited by Professor Priya Donti from MIT, and who's also affiliated with Climate Change AI. So welcome back November 2nd, and thank you all for today.